Thank you for the invitation. Thank you for the introduction. It's a great pleasure to be here. Today, my topic is the development of effective cross-linkers and their application in SLMS. SLMS had emerged as a powerful tool to study protein interaction and protein-protein interaction, especially for the study of protein dynamics and in vivo PPI network. The workflow of SLMS performed in a bottom-up approach. After cross-linking, the modified protein was digested and analyzed by mass. Cross-linker acts as our distance constant to provide space information. Major methods including X-ray, NMR, cryo, EM can apply as a high-resolution structure information. However, they need amounts of pure compounds, and it's hard for them to identify weak and transient interactions. SLMS can use in a mixture sample, and it's become a complementary method to address biological questions that other methods cannot answer. However, there are still some challenges for SLMS. First, the anchor problem, not search space, and also the low abundance in background peptides. Development of special cross-linker can conquer these problems. First, enrichable cross-linker have been developed. A cross-linker with a built-in tag is a popularly used affinity tag, as we know built-in has high affinity binding to threading. However, the bulky nature of built-in may affect the linking efficiency, and a two-step methods have been developed. Alkyl or azide were introduced to a linker, then they react with biotin through click chemistry. And this method is very useful now. And recently, phosphate-based cross-linker were also developed. We first introduced a phosphoric acid to a cross-linker. Then, immediately, a large group also reported a phosphate-based enrichable cross-linker called FOX. And then, our derivative of FOX, tetrabutyl FOX, have been reported by Professor Liu. She just mentioned this cross-linker yesterday. Undoubtedly, enrichable cross-linker is a useful method to purify modified cross-linkers from background. And the large question is the large search space, especially for the non-cleavable cross-linkers. An exhaustive compilation of all peptides leads to an explosion of the search space. Then cleavable cross-linker appeared. Each can cleave the pairs to two linear peptides, then it can reduce the searching space to a linear searching space. A lot of mass cleavable cross-linker have been developed. This is our overview of cross-linker applied to my biological applications. As we know, SLMS is moved toward conducting in highly complex biological systems. How to increase the identification confidence and minimize the searching space and time is very important. And our research interests focused on the development of phosphate-based enrichable and mass cleavable cross-linker. Also, the method to simplify the workflow of XMS. Actually, my background is chemistry, so I began my work from the synthesis of a library of microreceptors. They can use to probe the amino acids of proteins or peptides. We first developed a method to selective modification N-terminal lysine, cysteine, and disaramide residues of proteins and peptides. Then we developed a series of base microreceptors, then can use it to selective modification or special protein antibody. The most important thing for this method is the selective modification. In this research, we also find some linkers with high reactivity, so it's not good for the selectivity modification. However, it may benefit for the cross-linker for SLMS. This is just the point I entered into the SLMS. We choose one linker with high reactivity and introduce our phosphoric acid to the linker, and we obtained a phosphate-based enrichable and enrichable linker. As expected, this linker can target different amino residues, including lysine, cysteine, and histidine. And to our delight, we also find that this linker is mass cleavable through a retro microaddition. This is the new fragmentation pattern in MS2. When we applied our cross-linker to a model protein BSA, a total of 49 unique cross-linked peptides have been identified, including lysine to lysine, lysine to histidine, and histidine to histidine. Briefly, a multi-targeting mass cleavable and enrichable cross-linker has been developed. However, for this linker, there are also some limitations. First, the coupling efficiency is not as high as we expected. Second, the oxygen phosphoric bond is unstable. And the third, we cannot distinguish the endogenous and modified phosphorylated peptides. So we want to find more efficient cross-linkers. And then the Fox linker was reported. In variation of this cross-linker, we insert a stable carbon phosphor bond. Was more important, our phenoxyl acid bond was inserted to this cross-linker. We assume this linker will be cleaved in mass. Unfortunately, it's very stable. It cannot be cleaved in mass. However, in this research, we find another way to reduce surface space. Mathematically, if our cross-linked peptides detected, there are three situations. The first, both of the two molar linked peptides also can be detected. The second, only one of the molar linked peptides can be detected. And the third, none of the molar linked peptides are detected. We think the third one is rare since for the mass sensitivity, and we can reduce the searching space to the first two ways. Then we can the searching space can fall into molar linked peptide, and we build a molar linked peptide database. The major concern is that if the decrease in searching space will result in the loss of useful data, then we design three different search workflows based on the restricted database and the regular unrestricted database. The restricted database reduced the searching base to 40-fold. The result is that, indeed, the restricted methods led to the loss of intra-CS mass pairs. However, the searching sensitivity was significantly increased for inter-CS mass, and the 64 inter pairs have been found in our methods. Only 10 pairs were found in the regular searching method. We further applied our method to the existing method, including Pinninger-2 and Matter. These two methods identified 8 and 35 inter-CS mass respectively. Therefore, our method is very sensitive, and we further evaluated our data to our stringent database. Found that the identified PPI are reliable, highly reliable. Briefly, we proposed a decision tree search strategy to develop or reduce the space search method, each highly sensitive for the identification of intercross-linked peptides. We continue our effort to find mass cleavable linker. Since the phenoxyl ether does not work for the cleavable, we replace it with a benzyl ether bond. Yes, it can be cleavable. However, the cleave efficiency is not high. And what can we do now? We find another interesting thing. We find that the retention time is highly relative of cross-linked peptides and monolinked peptides. Our high correlation was obtained both for the training dataset and the test dataset. We further applied our method to a reported dataset, including FOX and PDSPE, and the prediction is also highly reliable. So we establish our new workflow for the SLMS. We use retention time as an extra filter, and it can remove the majority of false positive haze, and it facilitates the increase of intercross-link identifications. 19.2 with S35 inter-CSMS were identified by our method and the p-linker method. So we can see we use the retention time as an extra filter. It can reduce searching space and remove false positive hairs. Further, it can improve in identification confidence. We haven't gave up the development of mass cleavable linkers. Since the ether does not work well, we turn our attention to the microreceptors. A number of microreceptors, these microreceptors have been synthesized, and their reaction efficiency have evaluated on our BSA protein. And this compound was sent out with high reaction efficiency. And further, we incorporated our carbon forest bond to this linker, and our new cross linker was obtained. When we applied this linker we found that this linker can be successfully applied in a complex cell lysate. What's more, we found that this linker have two fragmentation patterns. What's that mean? The linear ions and the cross-linking perk ions can be detected in mass 2 experiments. This is very useful since it will not require a mass 3 experiments. Also, our heterogeneous cross-linker was developed. One use our microreceptor as our mass cleavable site, and another photoactive group was used to probe non-specific amino residues, and also it contains our archive for clinical chemistry. On the other hand, we also synthesized our phosphate-based clinic reagents. This kind of reagents have applied patents, and then we can use these two methods to develop phosphate-enrichable cross-linkers. And this cross-linker is extremely high efficient. 416 cross-linked pairs were identified involving almost all residue types. And the application of this cross-linker to complexity terms are now going on. Our brief summary. Our phosphate-based enrichable, mass cleavable, and multi-targeting protein cross-linker has been developed. Retromac addition mediated mass fragmentation is our new net for the mass, and our decision tree search strategy and retention time prediction method have been proposed to reduce searching space and further remove the false positive haze and improve identification identification components. New linkers with special fragmentation patterns and phosphate-based click reagents for enrichment also have been developed. Thank you for my team, thank you for my collaborators, and thank you for your listening. Thanks. Any questions? Yeah.
我没有完全那个明白哈，就是那个设计的那个 crosslinker， 它能够跟各种各样的氨基酸都反应吗？
对的。
包括那些惰性的那个氨基酸产生。
就是跟 SDA 有点像，它是产生一个卡宾。我翻到这一页啊，它是产生在化学的角度来讲，它是产生一个卡宾，然后这个卡宾是很活泼的，它是能够插入到任何一个碳氢键、氮氢键、氧氢键，所以理论上它是可以和任何一个氨基酸去反应的。
所以那个右下角那个图是不是展示说它各种各样，我看不清是各种各样氨基酸的那个频率能够鉴定到分？这个是基于交联还是基于一些那个，比如说肽段的那种，或者是氨基酸的那个氨基酸的那个它的实验？就这个是基于什么数据？是基于交联的蛋白的样品是肽段，还是说那个单个氨基酸？
这是在 BSA 上交联之后酶切肽段分析的数据。
哦，那这样的话，可能就是还有一个鉴定的问题，就是说这样的是否可靠，是能拿到这个数据，但是这其中有哪些是可靠的，哪些，可能我觉得这个需要仔细看看。
对的，是的，这个就是这个关于这个光交联，因为它活性非常好，它的确就是一个鉴定是它的最主要的一个问题。然后呢，其实因为这个它虽然理论上对每个氨基酸都反应，但是实际上它是有偏好性的。它对于含有酸基的，就是这种含有 COH 这种的是容易反应的，还有对于位组小的这种甘氨酸之类的是更容易反应的。
然后它反应之后那个产物那个结构到底是什么？
就是这个位点，就是这个最大问题就是这个位点要去一再的确认，它就是一个。不
光是位点，就是它是个什么结构？
就是
质量上面怎么？
质量上就是对于这个 linker 来说，它把这个氮气就是 N2 会失去掉，那形成一个卡宾，然后就插入到一个氮氢键，这样就是连起来。如果是羟基的话，可能就是跟氧相连了，是这样的。
哦，就是这种产物吗？有没有别的产物？
这个
就是会引起质量会不一样的，因为如果有别的产物的话，那个质量搜索的时候没有设定进去的话，可能就是有一部分没有找到。
它的最大的副产物是跟水抓水，但实际上它的反应，它的分子量是丢失是确定的，就是9减28。
哦 ，OK， 好，我没有别的。
我中间有一点没有太跟上，就是你那个黄仙乙烯那个交联集团在 BSA 上交联的都是 lysine 和 histidine 是吧
？lysine 和因为 cysteine BSA 只有一个，我们当时没找到，主要是 lysine 和 histidine， 对的。
哎，BSA 上 histidine 很多呀。
但是它是一个它都是 SS 的形式，就溜键，它不是一个单独的 residue， 它单独的 residue 只有一个34位的嘛。我们是没有这个蛋白没有处理，没有把它的球基给处理的出来，它是以溜键，所以它抓不住。
就是黄仙乙烯这个我们也做了，但是我们没做 BSA， 但是苯唑铂锰的那个我们做 BSA 了，那个和 BSA 上的很多 cysteine 都是可以交联的。
BSA 先要用还原才能把 cysteine 给裸露出来。但是因为我们这个是没有经过这个就 DTT 处理这个蛋白，或者说我们是先交联后面再处理的。如果用 DTT 处理，可以把这个 cysteine 给裸露出来，但是实际上我没有经过这一步，所以它只能抓这种原先存在的。
就是你后面那个打 residue 交联的那个图看不清，就特别小，你能不能到那一页？
好的。鼠标有点。
你这个交联的是不是主要是 tyrosine，aspartic acid 和那个 glutamic acid 还有 cysteine， 因为我看不太清。
主要是 E 是最多的。
就是YDEC 是不是？
差不多吧。E 还有 D 对的 ，D 和 E 是比较多的。K 也是有的 ，K 也可以对的。
哦，就是还有一个你合成了一系列的那个交联机，就是有好多黄纤乙烯的那些。
对的。
啊。
其实我们后面一直想做 enrichable 的，就是可负极的，因为我们做质谱是非常不专业的，其实用03引入到这个教练，其实是我们第一个发表的，当时我们是2月份出来的，然后 Focus 其实是5月份还是几月份才出来的，但是我们做的非常简单，然后我们第一审稿的时候就是有一点评价很高，说这个 idea 很好，但是我们做的就是非常烂，然后人家怎么改，人家总觉得你这个质谱做的太不专业了，但是的确我不是质谱专业的，然后Focus， 所以后面 Focus 的影响是非常大的，
就是你这一系列的是都合成了，但是 enrichable 的只做了最后那个，是吧？
是这样的，因为我们发现这个乙烯基黄酰胺的它的活性是很大的问题的，我们合成这一系列是为了找到一个活性高的，所以我们先合成没有带这个 enrichable 的这样一个 tag 的，然后先去评价它的活性，那么找到了一个活性高的，然后继续再去引一个，把我们的这个 就是磷酸基碳再引进去。
哦。
然后我们其实还发现这个问题啊，其实我觉得磷酸引进去是会影响它的反应活性的，因为我没有带磷酸的时候，这个反应活性很高的，带完磷酸之后，它的反应活性会受影响。那么一个可能是因为它这个电荷的原因和它亲水性的原因，另外一个呢，的确这个磷酸就是相当于刘教授做过的，磷酸之后就它不透膜。
但是就是你最后那个不带磷酸那个，其实我们把它叫做 PDES， 我们已经发表了，但是我们看到的它和 cysteine 的特别强。
cysteine 反应性肯定是最强的，在所有的氨基酸里面，亲和性最强的肯定是 cysteine， 但是因为 BSA 里面它都是成牛键了，所以它没有去抓 cysteine， 都是成牛键，它不是一个。
但是我们只看到跟 lysine 的反应性，但是跟 cysteine 差一个数量级，但是和 histidine 呢，我们基本上没有看到。
你们有分析吗？因为其实，这种它也是有活性有差别的。还有一个就是，其实我也想请教你一个问题，后面我们已经一直很困扰的，就是这种像 NHS 它不存在侧面的问题，因为它跟水就不稳定了。其实我们这个其实存在一个侧面问题的，它 molar 的话，它必须把另外一个去淬灭掉，不然的话它就有可能去和 N 端，就是煤切纸和钛端的 N 端去反应。我不知道你们怎么解决这个问题。
我们也中脂反应，我们用100毫码的 DTT 去中脂反应，浓度非常非常高。
那这不破坏蛋白的结构吗？
就交联完了嘛，是中脂反应嘛。
你这个侧面完全吗？
应该还好。
谢谢，我来问电商务，还有什么问题吗？谢谢啊。
我能问一个问题吗？多谢陈老师的精彩报告哈，就非常看着就是各种各样的 cross link， 然后那个应该是一个非常好的 toolbox。
对，我们因为主要是做化学的，所以我们主要是想从结构上去做这样一个研究嘛。
这就是什么时候能就是 commercially available 啦？就是我们如果说想用一用的话。
说实话，因为我们后续的相当于是一条腿走路，我的质谱基础实在太差了。然后如果说有质谱的愿意和我合作，我们愿意共同推进这个。其实我宁可知道我还是有蛮多想法的，在这儿还没有完全的讲出来。
我们这儿有这么多做质谱的老
师，
对吧？对。
所以很高兴有这么个机会，就是因为相当于我是另外一个领域的，能够进来，能够大家学习交流，是非常好的一件事情。
多谢，
好，谢谢。
多谢。